questions could be along the lecture, it could be in Portuguese or in English. So enjoy, okay? Thank you, Camilla.
Right, so today we're going to go more into details of planets and what they are, and more specifically in circumbinary planets. And yes, some other stuff about single star mother. As you might have understood yesterday, I like specific things. And here also I think that single star, they're boring, and like double stars, they're very cool, but yeah. Okay, so what is a planet? A planet is, by the definition of the IAU, so the International Astronomical Union, it's a body that orbits the sun, and it has sufficient masses to have to be in It's all right, it's all right. It's just weird. It's the first time I actually have something that is following me all around, so I wonder if you start like dancing the Macarena, what's gonna happen, but okay. It possesses sufficient mass to be in hydrostatic equilibrium, meaning that it's like a sphere. So definition forces present as a rigid body implying a rough, rounded shape determined by hydrostatic equilibrium. And the third one, it has to be sufficiently massive to be able to clear the orbit from residual debris. This is exactly the third definition. The third point is the one that decided that Pluto was discarded as a planet and it was just a minor body. So we have the planets in the solar systems. You might know all of them. But the solar system is not made just out of planets. We also have like minor bodies. For instance, we have the Oort cloud, which is, you can see the distance with respect to the sun. And we have the Kuiper belt. And then we also have some comets. Our teeny tiny Pluto is there. So when we talk about solar system, we do not talk just about the planets. There's a whole system that was formed. And we need to account for all of the minor bodies as well. Otherwise, if one day you're going to get to a department and you're going to have a solar system colleague and you don't mention, oh, you two asteroids, it's like recognize that it's a solar system speciality. Okay. This is also an artistic representation of the Milky Way done by National Geographic. I found it very, very cool because it tells you that like our probability of being here on this Earth is really, really teeny, teeny, tiny. In fact, we are at the moment here. So this is, well, Christina just told you about our galaxy. So this is the center. But you need also to think that to be able to host life, our solar system survived, didn't encounter many obstacles on its formation and evolution. And for instance, like we have our solar system orbit in the Milky Way, which is like very free from obstacles. So we don't crash with other stars. So we don't encounter other stars that destabilize our solar system and things like that. This is very important for being like having a stable planetary system. So yeah, we are away from dangers and we are away from stellar clusters, and yeah, that's another thing. Like, okay, fine. And then this is our solar neighborhood. This is also another peculiarity. So obviously we have the closest stars is Proxima Centauri, which is here, and then you have as a function of the different radius at the distance that this is 20 light years, this is 5 light years. So Proxima Centauri is just within this radius, and these are our solar neighborhood. But how do we see, indeed, the Milky Way on Earth? Have you ever had this wonderful opportunity to be in the desert or somewhere very far away from lights, city lights, to see that beauty. Yeah, because that's absolutely magnificent. So this was taken like in the national park, in the Arches National Park in the US. So this is basically the Sagittarius arm. So this is the center of the galaxy, and that's the Milky Way. Okay, but what is an exoplanet? We define a planet, but an exoplanet is indeed like a planet that is outside the solar system. So automatically that orbits other stars that are not our sun. A planet can be alone or also in a multiplanetary system like ours. And it can orbit also around two stars. In the case, we call it circumbinary planet or circumstellar planet. We'll get more on that later. So I wanted to show you the TRAPPIST-1 system here that was discovered. It was a very exciting discovery because it was the first the first extrasolar system that was with 7 planets. Like we never found this before. Like the mostly similar to our own solar system, and that's the comparison between the solar system and TRAPPIST. So you can see that TRAPPIST is so compact. It's around like a smaller star. It's not around a solar type star. It's around an M dwarf star, right? And this is the size of TRAPPIST here. You see? So that's the difference between like our solar system. So the diversity is very large about the architecture and always depends by the type of formation and evolution that these planetary systems had. Up till now, we have discovered, I checked this like 3 days ago, something like that. We discovered more than 5,700 exoplanets. And you can see here is a function of the discovery year and the method of the discovery. So you see that most of them are discovered by transit, because of course with the development of the technologies such as the Kepler telescope and now TESS telescope, you have many more detection by transit. And then you have also radial velocity, which is quite important. So the first planet was discovered by radial velocity. And then you also have a teeny tiny part of microlensing, direct imaging, and timing variation. So you see that it's exponential indeed, because when we understood where to look, and we developed the technology, it was much easier to find a new exoplanet. And here you have, as a function of, well, the parameter space for the distance, the separation of the planet from the central star, and the mass of the exoplanet. And again, like as a function of the method for the discovery. So transit method can find exoplanets that are very close to the star. So you see that it's like in days. Within 10 days, well, let's say 20 days. And then radial velocity can go a bit further out. And direct imaging, of course, it's just the wide orbits. And then you have some spots for the timing variation. The first exoplanet was found in 1995. Why is it not there? Well, fine. Yeah, exactly. But like, there's no tick. So I've just realized that. Yeah. It took a long time, but seriously, like people were looking for planets back in the 80s, you know. Obviously, technology was much different, but like you had these dedicated people that were like out there with their telescope, and they looked for it like for 20 years or more, and they couldn't find anything. I didn't put the slide; it was very fun, but they couldn't find anything, and it's just like all of a sudden they discover 51 PEG. But why they couldn't find anything? Because like formation theory tells you that an exoplanet needs to be far out, like very distant from the star. So everyone was looking just far away from the star. Just like, I can't find anything, I can't find any signal, no, not at all. And then in the end, it was just very close to the star. And they found the first one, so they started looking around close to the star. Still not understanding why, because the models did not tell you like why the planet was supposed to be there, right? So it was after many other detection that we understood that the planet is born on the outskirt of the disk, and then it migrates toward the star, right? So it was like, oh, hold on. And then they started doing a survey, like just looking close to the star, and then they found so many, like, and then, pew, you had the increase of the detection. But again, like believing, everyone was believing that it was, okay, let's go for with the models where we expect them to be, and nope. Okay, so which are the type of exoplanets that we have discovered up till now? With more than 5,000 discovered, obviously, we divided them in classes because they have a different formation, like their formation pathway is different depending by the class of exoplanet. So 30% is gas giant, meaning that basically they are giant and they are composed mostly by gas. Then 4% is terrestrial, so small rocky planets around, like similar to our Earth. Of course, it's very tricky to find terrestrial planet because they are teeny tiny, right? So in this slide, there is an observational bias, of course, because we are not able to find them. So that's what the percentage that we have on the whole population, right? 35% are Neptune-like. They're similar to Neptune and Uranus, and they can be ice giant, meaning that they're far away from the stars, so they don't receive much radiation, or they can be warmer, so like closer. But the warm ones are very rare. And then 31% it's made by super Earth, so as the word says, they are a bit larger than Earth. Between Earth and Neptune, we don't have any representation in our solar system, so that was another very huge discovery. It was like, oh my God, there's something we don't like, we were not expecting at all. And they can be like rocky worlds, but yeah, with a very puffy atmosphere. So the core is rocky, but then they have a puff atmosphere. Puff meaning like extended. Where and how do we find them? Okay, let's get more into the observational part. So we are here, that's the center of the galaxy. So we have discovered these exoplanets in the solar neighborhood because we use the light. We use the light, they're direct and indirect method, but use the light of the star. So of course, if the star is far away, I cannot see the star, so I cannot detect the exoplanet. So you see, you have a ring around our solar system of detected planet, and then there's this funky jet where we have discovered many exoplanets in this part, because it was thanks to the Kepler mission. The Kepler mission was just like staring for a long time in the same field. And by this has ended, but I don't know if, right, okay. No, I'm talking about Zoom. Right, I don't know. So by staring a long time in one direction, you could spot how, like, you can increase your signal to noise of the stars. So just like combining light curve, and then in the end, combining all the different light curves together, you could find exoplanets. So that's the only reason why we can see deeper and far away from us. This is like by transit and radial velocity and direct image and so on. And then we have the microlensing exoplanets, which are this teeny tiny dot until there. Microlensing is a very peculiar method, but it's very interesting because it's the only method that can help you find exoplanets around any type of stars and any size of stars. But I will tell you what is exactly the method later. This peculiarity is just like it needs a really like crowded background. It really needs a lot of stars in the background of between the observer and Okay, fine. You really need a lot of stars in the background, and then I will tell you why, but when you get to the method itself. So this is the reason why we find microlensing exoplanet just towards the center of the Milky Way, because the center of the Milky Way is full of stars, right? So that's easier. Like, you wouldn't be able to find the exoplanet by microlensing on this direction or in that direction. Okay, so transit photometry is one method, radial velocity, microlensing, astrometry, and direct imaging. The only direct method is direct imaging. All of the rest, we use the light of the star to detect the exoplanet. Okay, so radial velocity. Basically, again, it's a binary system with one star and one planet. So what happens is that the two bodies, they rotate around the center of mass of the system. And when the star is coming towards us, is basically we have a Doppler shift effect. So we see bluer lights, and then when it go further away, we have a red shift. In few words, basically, if you observe the spectra of the star, you see that the lines are shifty periodically, right, left, like blue, red. Okay, in your side, blue, red, blue, red, blue, red, and then we know that there is a body. And then we can measure the upper limit of the mass through that. So again, the first exoplanet, 51 PEG, was discovered by radial velocity. It was Jose, PhD supervisor, that discovered it, right? Toulouse, right, okay. So this is just a comparison of the planet. So our Jupiter is this side, and then we have a 51 PEG B. There's 47% less massive, but it's much larger. So basically, the density is smaller. And then this is the comparison of the star, the sun, and 51 PEG. Do you know, by the way, when you discover a planet, you call it the name of the star? And then you add a B. If it's the first one you discover, you add a C. If it's the second one you discover, you add a D. If it's the third one, and so on, right? Okay. And when it's a binary, then the name of the star is AB, uppercases. And then you add a small b, a small c, a small d. It's very tricky, but yeah, okay. Right, then we have transit photometry. So basically, it's a concept of occultation. So in here, it was a revolution because we could indeed measure the size of the exoplanet, because it's just the ratio between the surface area of the star and the surface area of the surface of the exoplanet. But of course, it's again, it's biased, because for the planet to eclipse the star, you need it to be coplanar. So it needs to be with an inclination that is almost 90 degrees for it to pass it. It's already finished. I'm just gonna go back. For it to pass in front. So I put this for a multiplanetary system. So you see that when the first planet, which is the largest one, it passes in front, you have... I'm sorry, just a second. Well, I was supposed to have all of the different light curves. I don't know why it's not working. Okay. Right, so when it passes in front of the star, it's a occultate light of the star, so you have a dip in the brightness, so you have it here. But then it might be that also it's going behind it. So we call it the first one, the transit, when it passes in front. And then you have the eclipse, where you basically here you measure the flux of the star alone, because everything is hidden. Of course, this is just in a case of a single star system. I don't really know why it's not appearing, the transit light curve here, but yeah. Anyway, the larger the exoplanet, the deeper it's going to be the depth, right? So if we have a small exoplanet and a large one is going to do this, and the other is going to do a tiny one. So by using this, combining it with radial velocity, we can have we can measure the radius and the mass of the exoplanet. And this was a real observation of the transit of Venus in front of the Sun in the XUV band, so extreme high energy. Of course, taken at different epochs. And then we have astrometry, which, again, the concept is more or less like the radial velocity, because it rotates around center of mass, so we use that. But astrometry, what it's going to do is going to measure the distances compared to other stars, in poor words. So also this is going to be a periodical movement. Yeah. So, yeah. With the transit method itself, you just know the radius, okay? Then you combine it with the radial velocity method, and the two of them together, they give you mass and radius. So, I like your question, because ideally you would say, okay, fine, I found a mass that is like below 13 Jupiter masses, so this is an exoplanet. And then depending by the range of mass, you can say it's a super Earth, it's a Jupiter mass-like planet, and so on. But yeah, it might be that you have, 0.6. No, it's fine. Yeah, no, this is the answer, yes. So you use both of the methods to trace down if which kind of thing is occulting. Because of course, like, you might have other bodies like brown dwarfs that are in a binary system with a star or other object. I don't know if you want to add something about it.
I mean, photometry could give us the detection, the rays, but you need spectroscopy to characterize, to know, you need radius and mass to see density and decide which planet it is. I mean, Earth-like or Saturn-like. So yeah, spectroscopy is fundamental on that as well.
Yeah, I didn't put like a plot of the radius versus the mass, but maybe like later I can show you like one other plot. I completely forgot. Well, anyway. Oh no, wait. Yeah, no. Okay, you understood the astrometry, right? The thing is, like, no exoplanet have been discovered yet through astrometry. We are waiting for Gaia. That is going to deliver a lot of exoplanets, but most of them, they're going to be giants and very close to Earth, because it's a teeny tiny signal again, so it needs to be big and close to actually see the variation in the sky of the location of the star. Okay, and then we have direct imaging, which is the only direct method. What happens is basically you use a coronagraphic mask to just cover the star, and then your exoplanet is gonna appear in the photo. So it's a matter of taking photos. Obviously, this is a simple case, but there are many different types of coronagraphy masks that are being invented and tested to be able to observe exoplanets at a lot of frequencies, right? Not just a one wavelength band such as the visible. Actually, exoplanet works much better in the near infrared because so between a star and exoplanet, who is the coldest one? Which one is the coldest one? Come on, don't be scared. I'm not here to bite you. Yeah, exactly. The exoplanet is the coldest one, right? So to see stuff that are cooler, you need to go in the infrared. So the peak of the spectral energy distribution for an FGK star is going to be in the visible. But then the peak of the spectral energy distribution of exoplanet is going to be towards the infrared, right? So if I go, right, so just this. So here we're going to have the star. So let's say this is the visible band. And then we are going to have the exoplanet that is, okay, it's fine. This is exaggerated, right? But like, you get what I mean. And then you have here the near infrared. So if I have to maximize my opportunity to find an exoplanet, where am I going to observe? So this is, well, like this is sad, and this is like, if I observe in the visible, I need to cover that much of a difference between the radiation of the exoplanet and the radiation of the star. But if I go here, I just need to cover this part. So it's going to be easier to cover the contribution of the star and then have a maximum contribution of my exoplanet because it's radiating more, and then I can see it. So that's why we go cooler. We go in the infrared and the mid-infrared. That's one of the fantastic thing of JWST because it's covering the mid-infrared, where you can do obviously galaxy and so on. But exoplanets are also cool. Yeah. So it's you have different type of mask. It's called coronographer. The simple mask, it's called Lyot mask, which is exactly this one. You have you just put stuff like you have a picture, and in your instrument, before taking a picture, you put like something that is covering the star. So this is the star, the one that you see here. You just cover it, and by covering it, you see what is around it. But then there are other methods and other coronagraphs, so for instance, that are more advanced, that, for example, the ones that are using in JWST, you have two different types. Lyot mask, which is this one, and then you have the four-phase quadrant mask, which are masks, but they are like slightly different made. You have a tiny offset within the mask that is going to help even more to decrease the contribution of the star. And what is very interesting about direct imaging is that, so let's say that this is like an adult exoplanet that is already formed, it has cooled down, and it migrated, and so on. But then this type of exoplanet that we see with direct imaging, they have just formed. So let's say that they might have like a contribution that is a bit higher. So that's why we see them. Usually they are all around young stars, so just formed. So if we observe through direct imaging, we see young planetary system. And still, the planet has to be far away from the star. I forgot to mention that. Because obviously it needs to be in a region where when I cover the star, I can disentangle them. Like, because if it's too close, if I observe them in the sky, they're going to be too close. Like, I cannot resolve one from the other. So if I cover one, I will cover the exoplanet as well. And also it depends by the kind of mask that you're using. So it's called inner working angle. There is a parameter that tells you like how far away you need to go. Like the mask is going to allow you to go to see exoplanets beyond the inner working angle. Okay? So they have to be on wide orbit, the direct imaging exoplanets. And this is indeed the example for HR8799, which has 5 exoplanets. So I have the B1, which was the first one detected, B, indeed, which was far away, and then technology improved, and we can go and find exoplanets that were closer. So we also have this tiny, tiny E that is here. But you see, this is one of the effects of the mask. It doesn't look like a normal star point source, because you put the different mask will have, well, this is also a treated image. So you remove, you don't only cover that. You first cover that, but then you subtract also other, you did post-processing of the image to clear it a bit even more, you know? So this is like, these are called speckles, the residuals and the stuff that you see. But then like the exoplanet come out very well. Okay, so let's move on now on exoplanets in a system with 2 stars. Wow, okay. We have the P-type exoplanet and S-type exoplanet. Again, one is P-type is called also circumbinary, and the S-type is called circumstellar. What's the difference? Basically, in here you have the stars that are in the center and the exoplanet that is orbiting around it. In here, you have an exoplanet that is orbiting one star, and this star is orbiting another star. So each one of the stars has their own exoplanet. It's not that the exoplanet is around both of them. Is this clear? Because this is important. If I have to explain that in the light of what we mentioned yesterday, usually this system, you have white stars. So everyone is evolving by their own way. They just have like a gravitational pull between the stars, but the planet is not affected because it's not affected by the gravitational attraction of the other star. So it just stays like with its own mother star, and that's it. In this case, the 2 stars are in the center, and then you have a planet. And in this case, it will be a hierarchical system, you know. So as I mentioned yesterday, you have the 2 stars that are in the center, and then the other that is far away that can be considered like a second binary. So you have the inner binary, we call it, and then we have the outer binary, which is the binary and the planet that are orbiting all together, okay? Right. Circumbinary P-type exoplanet. The first discovery was a Kepler-47 system. It was discovered by Kepler. It was the very first circumbinary exoplanet. Everyone got so excited because they couldn't believe that Star Trek was right. No, Star Wars, sorry, that was a bad citation. As we mentioned yesterday, there's this famous picture of the guy, Luke, with the 2 suns. Don't ask me more, because again, I didn't watch it. But yeah, that was the first discovery. It was very exciting. Yeah, indeed, you have the 2 binaries in the middle, and then you have the exoplanets in there. The interesting bit here I wanted to mention, oh yeah, they discover after that there's a third. I was like, oh, seriously? Okay, it has 2 exoplanets, sorry. So this is C and this is B. Yes, so C has an orbital period of 303 days. Ideally is in the famous habitable zone, but it's thought to be a gas giant. And then we have B. Sorry, I can't read on the other side. Okay, no, so B is in the inside because it's less than 50 days, and then you have C that is like 303 days indeed. You have a binary that's composed by a G-type star, so like the sun, and then an M-type star, which is on the bottom end of the HR diagram, so cool and teeny tiny. Okay. At the moment, we have discovered not many. So like compared to the 5,700, we only discovered these. So the blue ones are discovered by transit, and then the red ones are discovered by other methods, usually transit time variation. And then you have here, well, the stars in yellow, and then you have the exoplanet in blue. And the bar is the stability limit of the system. And you also might have an error bar on the separation from the inner binary. But why haven't we discovered so many? Indeed. I'll come back on that later. So between the circumbinary exoplanets that were discovered by Kepler, we have obviously a variety of dimension of the stars and also of the exoplanets, and you may see that it's not just one single exoplanet, but you have a multiplanetary system like Kepler-47 with three different exoplanets. Okay, so what are the properties of the known circumbinary exoplanet? Again, we're talking about a sample that is like mostly 20 planetary system, right? So we extract what we can from there. You cannot really do a population study out of it. We try to, but it's not really easy. So we don't know many things about that. Exactly because, okay, coplanar orbits. What does that mean? That basically they are all on the same orbit. Maybe there is a tiny variation, but it's the same orbit of the binary. So the binary is orbiting on one plane, and the planets are orbiting all over the same plane. We saw that binary mass ratio doesn't matter. So the mass ratio between the more massive star and the less massive star doesn't matter. We can find exoplanets around any type of binary mass ratio. Okay, fine. What is very important is, these are all information that we got from the transit sample. Binary orbital period, yes, it is very important. What is the orbital period? Basically, it's the separation of the inner binary. That one is important. And it's important because we find exoplanets that are only around specific type of orbital period. And we have just detected giant planets. We have never detected like anything that is smaller than than giants. So here you have the distribution of the the black one is the distribution of the single planet detection, right? So you have Earth, that is like one radius, of course. Then you have Neptune, which is around the 4 Earth radii. And then, so in here in the middle, all of these are super Earth, around single star, sorry. And then with a small sample that we got, we found that the occurrence rate of circumbinary exoplanets, it's exactly the same of the giants. So on this side, of course, they are all giant exoplanets. So the circumbinary exoplanets are all giants, and the occurrence rate is similar to the black line, which is the occurrence rate, well, the abundance, as you wanna use this word, of the giant planets around single stars. Any questions up till here? Yeah.
But does observational bias affect this plot, or like can you correct for it?
We can't. At the moment, we can't because we don't have much information to correct for it. We're trying. The thing is, like, these 13 exoplanets were found by transit. But transit, it's a bias method. If you start observing with radial velocity, then you can find exoplanets that are, you can find more exoplanets. The problem is, like, these planets are in a hierarchical system, so they are far away from the binary. And being far away, to be able to prove that it's an exoplanet or a body that is like bonded to the binary, you need to have, well, that's in general, you need to observe it for at least 3 planetary periods. So if it's one planet that has a 1-year period, let's say, around the binary, you have to observe for 3 years before declaring it. So we are trying to correct it using other methods that are more time-consuming. Yeah.
The blue vertical line is individual system, and
so yes, these are the known system, the 13 transiting exoplanets. Yes.
Oh, okay. Thanks. So the point with the bar
That's the average. So
is
yes.
the average. Okay.
Yes, that's the average over the radius of the planetary radius. And these are the reference papers of.
Thank you.
On top of that, it's very few people working on this because everyone is just disregarding binaries because they are more complicated to process. Okay, so circumbinary planets are the circumbinary planetary systems are the perfect astrophysical labs because by studying the formation of these systems, you can also understand the formation. Well, you can also understand the systems around single star exoplanet. What with like Ian did in this work, it was indeed to find that he was observing like planetary disk around binaries and with ALMA, and then he found that there is indeed the circumbinary disk where you can form exoplanets are misaligned, like it can be misaligned, and this is strongly dependent on the orbital period of the host star. So depending on the orbital period, your disk will have a different inclination, and automatically, if from this disk an exoplanet is born, you will have a very different inclination of circumbinary exoplanet. But yes, exactly. So the limit is like closed binaries, they have a disk that is lying with the orbit, and then binaries with period longer than a month, they have misaligned disk. But why is this important? Like, this is very nice, because in the moment that I have a lot of misaligned disk, it tells me that we can have a lot of circumbinary planets that are not coplanar with the star. That means that I cannot see them by transit, so that's why I don't see them. We only have 15. But it tells me that the inclination of the circumbinary planets is isotropical, right? Can be isotropical. What does that mean? That it can cover all the type of inclination, okay? And there is a work by Armstrong, 2019, that tells us that the occurrence rate of exoplanets, circumbinary planets, is exactly the same one of single stars if they are all coplanar. But if they are not coplanar with the binary, then the occurrence rate of circumbinary exoplanets is much larger. So the idea is like we are truly not seeing them, we are truly not detecting them, but circumbinary exoplanets are much more or the same frequency or much more than those that are orbiting single star exoplanet. And that's why I find that it's a really nice population to study and try to detect, because if you study this kind of systems, then you have a very good, like, you will have a better understanding of also exoplanets around single star systems. Okay, so let's go into radial velocity method, exactly like taking up on your question. Transit, we saw that is not very efficient. So these colleagues of mine, this was a courtesy of Matt Standing, but they built up this radial velocity survey that is called Binaries Escorted by Orbiting Planet Survey, the BPOP survey. And they have been observing for, I think, like at least the last 4 or 5 years. So they just released the BBOP 1C. So that was one of the detection, and together in the same system with BBOP 1B. And here, these are all the new detections that are still not released. They will come out in the upcoming months. But you see that what the radial velocity is giving us compared to the transit that it was before, it was just like a giant exoplanets. Most of them are in the Saturn area, right? So again, we are trying with new methods to find other, like increase the sample of circumbinary exoplanets, and we are starting proving that we can have also planets that are not giants, but also subgiants, and like, well, they are still giant, but like we are going down in the mass range. Okay, So these are the current occurrence rate, well, back in 2027. So the number of exoplanets, the circumbinary planets that you might have as a function of the mass and as a function of the separation from the binary. You see that the numbers are not that big, but this is just specific of this survey, the radial velocity survey, right? Yeah, okay. Again, like I said before, that these planets are more difficult to observe because they are further away from the binary. But why is that the case? Simply because you have an inner binary that's like perturbing the third body, the exoplanet around. And so you need a planetary system to be stable, to be detected, you know. So back in 1999, Holman and Vigert, they worked on the stability criteria of p-type architecture, and basically there is a limit, which is a function of the inner binary separation, after which exoplanets can be found. More specifically, well, here I put the whole equation, but it's all of a function of the inner binary, the eccentricity of the inner binary, and then the binary mass ratio, okay? If we have to simplify it, when you have coplanar orbit, exoplanet will be found after this critical separation, which is between 2.5 and 4.5, the separation of the inner binary, of the two stars. For long-term dynamical stability, it will have to be much more. So usually the period of the planets needs to be after, like the planets will be found with a period 4 times, 5 times larger than the period of the binary. So this helps us to target how long we can observe one binary system, for instance, one binary. Of course, here I'm just referring to perturbation of the planetary system. I'm not talking about perturbation given by external bodies, so an encounter with another star that is gonna destabilize the system, right? But again, after formation, there might be a problem, a moment of chaos where you have planet scattering, and then we talked about this in the last lecture, and then it gets stabilized. But obviously, the orbit of the exoplanet will be, again, like with a period larger than 4 and 5 than the binary period. Okay, another aspect that tells us that the circumbinary exoplanets are a bit further away is the fact that formation in situ is extremely difficult. So here you have a simulation of the formation, or like what's happening to the disk when you have the inner binary, and at different times. So you have 120, 250, and so on, right? So you see that there's a creation of this turbulence, and so you cannot really form exoplanets that are close to the binary. So we know that exoplanets form circumbinary, CBP form at least at like separation that are more than 4 AU, and then the migrating worlds, okay? This was like, again, another, after they discovered Bebop 1b and 1c, they tried to do a formation simulation of these planets to understand indeed if they were to form in situ or not. How do you read this plot usually? So these are called growing tracks. Maybe you saw them with Vladimir, it's possible? I don't know. So you have your seed, you put your seed at in your disk at one separation, and then you let the simulation carry on, and then you see like if the seed is growing in mass, for instance, and then like where it moves in this with the distance and with the mass as a function of the disk, right? Because the disk has a time scale. At some point, it's going to evaporate, so also the formation is going to stop because it doesn't have the planet doesn't have any more material to use to grow. And in this simulation, indeed, they found that these are the official separation of Bebop 1b and 1c and the official mass observed. And then they found that this point and this point indeed can reproduce the formation. So they start more or less from here. So again, it's a track that of an exoplanet that was formed around 8 AU. Well, I'd say 7 and 8, or both of them, of separation. Any question up till here? If something is not clear, like, just tell me. I mean, I can try to explain it with different words. Okay, so orbits are piled up. What happens if they form far away, again, in the disk, and then they will just, like, move towards the inner stability limit, and that's what we see with the observation. This work was done before this one. So you have that this is a stability limit as a function of binary semi-major axis and planet semi-major axis, and then you see that, like, a lot of planets are just like the transit ones are piled up on the stability limit. And then later on, in 2020, they did with the new data, and then they saw that the exoplanets are basically lying on these lines. So this is 5 times the binary period, and this is 7 times the binary period, which is more or less what it was expected from the stability limit criteria. So what we understood is that they form far away, and then they migrate, and then they stabilize around the stability limit. Okay, so let's start getting into the evolution of planetary systems, right? Yesterday I mentioned, well, I think you might know it very well at the moment. So you have your star that is evolving out off of the main sequence, is becoming a giant, and then you eject the planetary nebula, and then it becomes a white dwarf, right? Let's imagine that you have an exoplanet around the star, right? So what happens to this exoplanet or exoplanets when the stars evolve off the main sequence? So just to give you an idea, these are typical values for a sun-like star, and have a look at the radius, the evolution. So in the main sequence, it's 1 solar radii, then you have 150, and then you have that is decreasing again in the horizontal branch, which is here, and then you go up to 200 solar radii in the asymptotic giant branch, right? So what if you have an exoplanet at 100 solar radii from the star? What do you think is going to happen? I'm just talking about the single star case, because this is like single star case. So I have an exoplanet that is like 150 solar radii, separation from the star, but then my star is going to go up to 200, right? Ciao, exoplanet. I was like, literally like destroyed, engulfed, eaten, Game of Thrones again, you know, like a distraction. So it's tricky because it depends by if an exoplanet survives, it depends by the initial separation and the mass of the exoplanet. Okay, let's go more into detail. Why before discovering them? Because now we have 4. Yes?
The first exoplanets discovered is pulsar binary exoplanets. So they have passed had evolved through main sequence. Out of main sequence evolution of 2 stars. So you know the typical distance of this planet?
Are you talking about the pulsar with the white dwarf system that has two exoplanets? That one?
No, the first one in 1992, I think, is a pulsar binary.
Yeah, see. Yeah,
so the planet have to survive at the evolution of 2 stars. And
yes, so you're definitely right. And let me mention that, yes, I said that the first exoplanet was 51 peg. In reality, he is right. It's just that no one really cared about that exoplanet because it was around a star that is like emitting so much radiation and pulsar. So I was like, oh, who cares about that? It's like a dead body, this exoplanet, we don't care. And they just moved on, just like disregard this poor guy like detection, and it was very sad. But now it's coming back on. I have a problem reminding like which kind of system you're talking about, because I have one pulsar system in the lecture. So I just need to double check and come back to your question for that. But it's towards the end of it, like we can talk about that. And I will go into details about the separation of those exoplanets in general, not just for that system.
Okay, thank you.
So how did we know that we had that planets might have been around the white dwarfs? So again, white dwarfs, they are very end of the star life, right? So they are old system. So we had hints that we could have exoplanets around white dwarf, but we never found it. Well, I'm talking about like 4 years ago, right? So one of the hints was that we could find white dwarf pollution. What is that? Basically, I mentioned yesterday that like the atmosphere of the white dwarf is usually hydrogen or helium or carbon. We don't have any metal on the white dwarf. And if we had any metal, the gravity of this body, it's too strong that basically it's like putting a mercury inside water. So it's just gonna fall down automatically to the bottom. Like you will not see it in the atmosphere of the white dwarf. But then all of this observation found out like all of this 25% of between 25 and 50% of all of the white dwarfs that we were observing had a contamination of metals. And it's like, it cannot happen. Like, I mean, if you that metal is going to fall down and that's it. And no, they kept seeing and seeing and seeing. That means like there was something that it was contaminating, polluting the atmosphere of this white dwarf with metals. And what could that been? Well, they had different kind of origins, but the most believed one is that you have an exoplanet, giant mass exoplanet, that is like a bit further away, and is acting like a slingshot. So slingshot is, for those of you who doesn't know, you put a pedrinha, né, no teu elástico, e pum, assim, né? So basically, it was acting as a slingshot, throwing debris and planetary residuals and rocky things like on the white dwarf. So it's just like contaminating it. So I could see the metals every single time in the atmosphere. And so that was one of the ideas, like, no, we definitely have planets that are surviving the evolution. Let's go and try to find them. And then we found them. Okay, so planetary systems can evolve. But of course, well, they evolve, but they might find engulfment, which is they're eaten by the star. That is like getting larger, and then they can be ejected. And in that case, they are going to enter into they're going to give more numbers to the free-floating planet population. Because you might not know, but we have planets that are just floating around. They're not bound to any star. And then they can also collide with other planets, creating a larger planet, for instance. Or they just get distracted. One of the effects, usually, of the evolution of the star is indeed the orbital expansion of the planet. So if the planet was 150 solar radii, when the star it started growing, like it's also like the planet, it's gonna migrate outwards. And obviously, these are the clue points where things happen. Okay, so do planets survive the red giant phase? You have the two options, like in the single star system and the binary star system. Now, I really want to pick your brain here. So tell me what you think about it. We just need to answer the question. I mean, like, it's fine. I told you about the evolution about binary stars, right? And I gave you the example of the single star before. Yeah, you want a chocolate. That's exactly the point. I mean, they can survive in both cases, but let's go more into detail, right? So you have, in the single star case, the star expands. It engulfs the planet. Ciao, planet, right? That's what I mentioned before. Sometimes it can engulf the planet and the planet can survive, but it depends by the mass of the exoplanet and so on. In the other case, you have indeed like the formation of the common envelope, and automatically, given that the star is not allowed to just go far away like where she wants, the planet is like has higher chances to survive. Of course, this is not well done, because in this case, we would have that this planet will be a bit further out of the orbit automatically because of the effect of the evolution, so you will have a tiny bit of expansion. But that's exactly the concept behind it in a very simple word. So, do planets survive the distinct phases of stellar evolution? That's another question for you. Yeah, exactly. Which type of planetary system have better chances to survive? Around binary stars, indeed. So this is the theory, but like, can we see that in observation? Yes, we can. So we have 4 planets that have been found in a very recent, well, apart from like 2008, yeah, but okay, fine. This was a very far away, so I don't know why it wasn't something so interesting at the time. We have 4 planets around a single star. We have 2 planetesimal. What are planetesimals? They're just like rocky bodies that are not really planets, you know, something destroyed that is orbiting in a periodic way, the white dwarf. But then in the binary star case, we have 5 planetary systems with a total of 7 planets. And then we have 5 planetary systems with 8 planets where the star is not yet a giant white dwarf, but has completed the giant branch phase. Okay, so also the observation are proving that we get that planets are more likely to survive the binary evolution. Okay, right. So this is to come back to your questions. I wanted to mention this because obviously it's very important. Single star or binary star is it's still very important. You have the so-called tidal engulfment radius that is a function of the stellar mass. Right. So here you have, so the 3 columns are the function of the solar mass, so one solar mass, 1.5 and 2. And if I recall correctly, it was super Earth and, no, that's the opposite. Super Earth and Jupiter and Jupiter-like planets. So it also depends by the mass of the exoplanet initially. What is the tidal engulfment radius? So this is the evolution of the star, like doing like the evolution of the radius of the star as a function. The variation of the radius of the stars is a function of the evolution of the star, right? Okay. So you see they are different depending by the initial mass of the star. And the red lines are the separation at which, if I put one teeny tiny planet, well, okay, here, a teeny tiny planet, is just gonna, at some point, crash against the stellar radii, okay? So while the black lines is where it's not crashing against the stellar surface. So here, for instance, like you, for one solar mass, well, I'm gonna go here. For 1.5 solar masses, you have that the planet needs to be at least at 3.5 AU of distance to survive, a giant one. While here, it has to be, or maybe it was the reverse. Sorry, guys, I don't remember. It was just a difference, first line one and second line the other one. While here, the planet has to be at 2 AU separation to survive. And all of this for the three type of stars. So you see that for two solar masses, at some point, like you also have a gravitational pull, you know, because it's higher. So even here, like the planet, the last red line, is gonna like get pulled towards the surface of the star, and it's gonna crash and get destroyed. This for like 2 solar masses, and then the same work was done by Veras for larger larger stars, so 6, 7, and 8. And yes, you can see also that there's for Jovian. Oh yeah, okay, so that was Jovian definitely, and this is super Earth, I agree. Okay, so for Jovian exoplanets, you have to be at distance like 5.5. For terrestrial planets, you have to be at distance 3, and so on. Well, larger than that. Okay. Yes, so with microlensing and with my colleague, we found this exoplanet that is a giant exoplanet that is orbiting at a separation larger than 2.8 AU. And it was a very, very nice discovery because it was the first time that we could find an exoplanet that it was farther away from, not very close to the central star, and it represents basically the future of the solar system. It's an exoplanet that survived the tidal engulfment radius. It's around a single star here, this one, that survived the tidal engulfment radius, and obviously it had possibly an orbital expansion. We don't know exactly where it is because it's a microlensing observation, so it doesn't give us specific details about the characteristic. But we got a JWST proposal, so it's going to be observed in September. And we are going to have more constraints on that, especially because 90% it's a white dwarf, but it could be a neutron star or it could be a black hole. In any case, it's going to be very interesting. So it avoids tidal engulfment, and we're still having an observation that tells us like how the planet, what's the current separation, will help us constrain the models that we have. So it's again the same game of observation and theory. And the mass of the progenitor star was probably less than 2 solar masses, because what we found is like the current mass of the white dwarf is 0.53, something like that. Okay. Right. I think I'm gonna have, well, because the class is, I have more things, but I can carry on like tomorrow. Yeah, so I think we can finish here. It's a long topic, and I want to go more into detail of the theory, but maybe we can just finish tomorrow. So if you have any questions up till now.
So let's thanks. Thank you, Camilla. So questions, please, comments?
Takeaway points. Planets can survive, and they have higher chances to survive around close binary stars.
So, okay, over there, good.
Hi, thank you for the lecture. So you said that planets can survive and eat more easily in binaries, but they also migrate in this phase. Can you comment about that?
You mean during the evolution?
Yeah.
Yes. So the effect that we saw in the simulation is that when the star starts to evolve, you have a lot of production of stellar wind, which can also be called Yeah, well, you have a lot of stellar wind, and automatically is like destabilizing the orbit of the exoplanet, so it's migrating outwards. If the wind is adiabatic, the usual expansion is 4 times the initial, like it expands like of a factor of 4, the initial orbit. That's if the wind is adiabatic. If the wind is not adiabatic, then you have a much larger expansion. And also you can have effect of evaporation, of course, on the exoplanet. So as in evaporation in terms of the planet is going to lose mass as well.
Thank you.
Other question? People are hungry, right? Yeah, Camilla.
Eu vou falar em português mesmo.
Tá.
Você comentou sobre os diferentes tipos de planetas circumbinários, o que orbita cada uma ou o que orbita o sistema total, mas tem, por exemplo, algum método de detectar preferencial assim para cada um desses?
Então, os planetas que são circunestrelar, eles são muito mais. Eu acho que são 100 ou algo assim, são muito mais. Mas é porque aí o planeta está bem pertinho da estrela, né? Então, dá para fazer com trânsito, é muito fácil, né? Sim. Então, isso é como se for aproximado, né? Como se for um planeta que está ao redor de uma estrela síngula, né? Mas o problema está quando você tem uma binária por dentro, então o planeta automaticamente está muito longe, e então, se for longe, trânsito não é o melhor método, né?
Obrigada.
Last one. So I have one comment about your planet, this pulsar planet, right? It's 1992. It's an extreme planet that is a little bit different from the white dwarf planet, because probably these planets are reformed. I mean, the white dwarf planets survive, but the pulsar could be formed in the supernova process, right? So it's quite different, the origin of one for the other one. So yeah, this exotic planet is quite nice now. People are so interested in that. So I think in the next years, we will see more of that. Yeah.